antiderivative part 2, initial value problems. Initial value problems. Okay, so let me explain that to you the best I can. Sometimes students ask me when I'm going over these antiderivatives, Professor, this is an introduction, but introduction to what? Well, this is an introduction to what you're gonna do carefully and in details in Calculus 2. When you can take Calculus 2, it's all about antiderivative integrals. So there you will do these things in detail. Right now, it's just an introduction, okay? So we are learning how to take the antiderivative of some basic functions, right? Yeah, that's the idea. But now, once you know how to take antiderivatives, then turns out you can use these techniques in order to solve what mathematicians call initial value problems, And what is an initial value problem? Well, it's a problem in which they give you the derivative of some function that is given together with some initial input output computed somehow. For example, here in this problem, they are asking you to, well, they're asking you to consider that the derivative of some function is 6x squared, and this is the initial value that they give you, f evaluated at 1 is equal to 5, and the challenge is to find the function, right? The function whose derivative is this and satisfying this condition. And you may say, Professor, we know how to take antiderivative. Why we need this extra condition? Turns out with this extra condition, you will be able to find the constant. That C that we've been writing a lot, right? Plus C, plus C, plus C after the result of our antiderivatives. With this condition, we will be able to find the value of that constant C, okay? So it says here, right? Given this derivative such that f of 1 equals 5, is it possible to find f of x? And the answer is a big yes. I will show you how. Look, derivative of f equals 6x squared, then f of x is the antiderivative of 6x squared, right? So we can start by taking the antiderivative of this function 6x squared. So let's start with that. At least to know what is the family of functions whose derivative is this, right? So if you take the antiderivative of this, well, we take this constant outside. This will be 6 times antiderivative of x squared. Using the power rule, we can say that this antiderivative is going to be x raised to 2 plus 1 here, 2 plus 1 here, right? Plus a constant, right? Plus a constant. F of x equals 6. X 2 plus 1, 3 over 3 here plus a constant. 3 into 6 is just the number 2, okay? Plus a constant. Professor, but we just did this before, right? What's new? Well, the new thing is that once you get to this point, right, you have found the family of antiderivatives whose derivative is this 6x squared, right? The family of functions, right, whose derivative is 6x squared. But now, considering this initial condition, right? F of 1 equals 5. I will show you how it's possible to find the value of the constant. F evaluated at 1 equals 5. So, F, right here, right? Now, F evaluated at 1 is equal to 5. This information is given, right? So let's use it. So what you do is this, F evaluated at 1, on one hand is this, right? 2 times 1 cubed plus C, right? I'm replacing X with 1, right? But on the other hand, they are saying that somehow this is 5, right? So write 5 there, equal to this. And this, guys, is giving me an equation, just to solve for C, right? So now, solve for C. So it's possible to find the value of this constant, right? So minus 2, minus 2. C equal 3. Now that you have found the value of C, then you can say that this function is no longer a family of functions, right? A family of functions of this form. Instead, it's this unique function, right? Then f of x is equal to, this is, let's do a substitution here, it's better if simplify. This is just 2x cubed plus c, right? Yeah, better here. C was found is 3, so I can say that f of x is this function, concretely, 2x cubed plus 3. You follow, guys? So it's possible to find the function, right? Because now we know the value of the constant. So this is the whole idea of these initial value problems, right? With information about the derivative, with information about an evaluation of the function, you can find the actual function. Okay, so now problems like this, the ones that I just described, are called initial value problems. Shorthand for initial value problems, IVP. IVP. So to solve an initial value problem, here mathematicians give 2 steps. Follow this method. First, as I did, right, integrate or take the antiderivatives. And this could be done as many times as needed. I will show you that sometimes it might not be enough to do it once, you might have to do it twice. And second step, use the additional information to find the value or the values of the constants, right? That's, in this case, remember, we use this information and we were able to find the value of our constant, right? So we have to do that. So let's follow these guidelines and let's solve this initial value problem. Suppose they say that the derivative of some function y with respect to x is equal to sine of x. And in addition to that, you know that the function y evaluated at 0 is equal to the number 5. Then solve this initial value problem, meaning find the function y. Find the function y, okay? So we're gonna do that. So we start by saying, right, that y, since the derivative of y is equal to sine of x, must be equal to the antiderivative of this function sine of x, right? Start with that. But now, what is the antiderivative of sine of x? Yeah, anybody could tell us what is the antiderivative of sine of x? And let me warn you, it's a little bit tricky, right? So you can look at your sheet.
Cosine of x.
Yeah, someone said cosine of x. But notice, if I take the derivative of cosine of x, remember? Yeah, we need a negative because when the derivative of cosine minus sine, remember? If you look at the sheet, it's negative cosine of x. So be careful with that sign, guys, okay? Minus cosine of x, because the derivative of this is the one that works, right? Remember, okay? Minus sine, and then this is sine, it checks, right? This is it. Now, to play safe, I would say always check your sheet with results here, right? Look, the antiderivative of sine minus cosine plus a constant, right? Very good. All right, so minus cosine plus a constant. Yeah, good. Now, the goal is to find this function y, not in terms of constant. The goal is to find the function uniquely, right? Not as a family. So we use now this part, this extra information that they're giving us, right? We're gonna do evaluation at this function y when the input value is 0 should be in one hand this, right? In one hand this. I substitute 0 instead of x, in one hand should be this. But on the other hand, they're telling me that this is 5. So put 5 there and get yourself an equation that you can solve for c. Cosine of 0 is just 1, right? 1 plus c. 1, professor? If you want to double check, use your decimal scientific calculator. Cosine of 0 in radians, 1, or even in degrees, 1. All right. Yeah, so this is it. So then adding 1 to both sides of the equation, we can find the value of C. So C ends up being equal to 6, right? 6. Now we found the value of C, right? Is 6. But immediately, once you do that, put this value of C in here. Then you can say Y is completely determined now, right? It's minus cosine of X plus 6. This is a function, okay? This is a function. So later on, guys, when you move on and study, you know, more mathematics deeper, what we just did is a very, very basic example of they call a differential equation, because the result of my equation is no longer a number, it's a function. So it's right for you to know. Yeah, but these are the 2 steps it takes. You get your function, you're done. Very good. Here is another one, but probably before I move on, maybe I should let you practice. Yeah, let's practice here. Let's go to the worksheet and then we'll go over other forms. Okay, can you try this? Yeah, it's a little bit tricky, there are 2 functions. Yeah, maybe I should do one for you and then I will ask you to do number 2, okay? Let me show you how we can solve this initial value problem. In this initial value problem, they're telling me that the derivative of this function is this. I should write here. Derivative of the function s with respect to t equal cosine of t minus sine of t. And they're telling me that s evaluated at pi over 2 is equal to 6, right? This is an extra condition. So I start by saying that s, since its derivative is this, should be equal to the antiderivative of this guy. Antiderivative of this guy, right? We're going to do that. But that shouldn't be difficult because we learned that these antiderivatives, they can be distributed over a difference, right? So I end up with the antiderivative of cosine of t minus the antiderivative of sine of t dt. Right, dt here. But now, what is the antiderivative of cosine? Anybody could tell me this? The antiderivative of cosine?
Sine.
Sine. Excellent, excellent idea. Very good. Sine, right? Sine. And the antiderivative of this sine. What is this?
Minus cosine.
Minus cosine. Excellent, excellent, right? Be careful there, guys. Now, in the end, when you simplify, you get sine of t, is that the constant, right? Plus cosine of t plus your constant, right? Your constant here. Now, the challenge is to figure out the value of this constant so you can determine this function completely. They are saying that in one hand, s evaluated at pi over 2 is going to be sine of pi over 2 plus cosine of pi over 2 is just a direct evaluation, right? Plus a constant. But on the other hand, they're saying that this guy is 6. So this guy is 6, sine of pi over 2. Sine of pi over 2 is 1. Cosine of pi over 2, 0. If you cannot recall that in your calculator, right? Sine of pi over 2 in radians, right? In radians always, this computation, 1. And cosine of pi over 2, 0, you will see. 0, right? These 2 guys. So bottom line, 6 equal 1 plus c, subtracting 1 in both sides, c equal 5, right? C equal 5. We found the value of c, so right away, put it here. And then you say, then, finally, then, my function is completely determined. Look, sine of t plus cosine of t plus the value of c5, right? Yeah, I figured out the function. That's it. So this is number one. So be this. Yeah, now this one is similar. Probably you can try this. Yeah, I think yes, there's two. Yeah, probably you can try this on your own. Yeah, so do this, please. Then we'll move on. Can you try this? Derivative of s with respect to t equal cosine of t minus sine of t, and s of pi over 2 equal 11. Mhm. Mhm. Very good, guys. Yeah, I see students getting ahead of this. Number two. A lot of students are posting. Yeah, very good, CG, Grace, Sarah, right? Yeah, very similar. So let's just do it quickly, right? S equal the integral or the antiderivative of this. But this, when you take the antiderivative, when you distribute, right, over, is the integral of cosine, which is sine. Yes. Sine there. This is no longer needed. Minus integral of sine minus cosine, right? Of t, and plus a constant. But this ends up being sine of t plus cosine of t plus a constant. Now, on one hand, s evaluated at pi over 2 should be sine of pi over 2 plus cosine of pi over 2 plus a constant. And on the other hand, they're telling us that this is 11. Sine of pi over 2, 1. Cosine of pi over 2, 0. Solve this little equation. You will discover that C is equal to 10. Once you get that, you put it here, and there you have your function completely determined. Cosine of t plus 10, right? Very good, guys. This is it, right? Very good. Excellent, excellent. All right, moving on. This problem is a little bit tricky. Let me see if I can show you this. Yeah. Yeah, let me show you quickly another initial value problem. This time they are saying here that the derivative of y with respect to x is equal to x raised to minus 3. I'm just putting this up, plus x. And they are giving me this extra condition. The function evaluated at 1 is equal to 2. So start by taking the antiderivative or the integral of this function, right? What should be that? Well, integral of this part will be x raised to minus 3 plus 1. Minus 3 plus 1 is going to be minus 2, right? Minus 2. Minus 2 on the top, minus 2 on the bottom. Plus the integral of this part, integral of x raised to 1. X raised to 1 plus 1, 2 over 2. Plus a constant, right? Plus a constant. This is y. Now, in one hand, if I do the evaluation of this function at 1, I'm going to get this, right? Plus 1 squared over 2 plus a constant. On the other hand, they're telling me that this is just the number 2 from here, right? Yeah, maybe highlight. I should highlight this so to realize where this came from. This 1 raised to any power is 1 minus 1/2 plus 1/2 plus c. Look, c equal to, right? Yeah, I see some students already figured this out. Yeah, CG. Yeah, we're headed there. Very good, very good. Yeah, very good. Right? Yeah, C is 2. Once you have C equal to 2, quickly put it there. And then you will have your function, right? So finally, y equal minus 1/2 multiplying x raised to minus 2. But this x raised to minus 2, you can put it down here as x squared, right? Then plus x squared over 2 plus the constant, but the constant is 2, right? 2, that's it, right? And this is a perfect match with A right here, right? Very good, that's very good. All right, so now this one is similar. So you can do it at home. This is one, right? Instead of 1 over x cubed, x raised to minus 3, and do this process, right, as I did here. Let me see other form. This one similar too. Instead of this, you can write x raised to 1/2, right? So yeah, this is this. This one is I think trickier because it deals with second derivative. Second derivative, and then we will go over the problems related to physics. So let me explain to you number 8. And then, yeah, it's a very long. Yeah, probably we should secure this part first and we can go back to this, right? Yeah, we can go back to this. Yeah, let's explain this part first. Yeah, is sometimes, remember the method says that you might have to take the antiderivative twice, right? Twice. What does it mean? Well, some initial value problems will need this process to be done twice. But first, let's start with what is simple, just an applications to physics, where you have to take the antiderivative just once. This is this and this, right? Let me explain that to you nicely here in the lecture, and then I will explain to you what to do in case you need to do it twice. Applications to physics. Giving s of t a position function, right? A function that gives you the position in terms of time. We learned so far that the velocity is given by the derivative of the position function, right? And also we learned that the acceleration is equal to the derivative of the velocity function or the second derivative of the position function, right? Equivalent. Good. Now we are doing this process backwards. So if, let's say, I want to get the position function from the velocity function, then I have to take the antiderivative of the velocity function, so I can get the position function plus some constant, right? Similarly, if I want to get the velocity from the acceleration function, I have to take the antiderivative of the acceleration function. That will give me the velocity function plus some constant. Now, finding these constants will require some extra information. I will tell you how you can use that extra information in order to determine completely velocity and position function and velocity from acceleration, or position function from velocity function. Example here, suppose they give you the velocity function and they give you this extra condition, the position function evaluated at 0 is equal to 13. And they ask you to figure out what is the position function, right? Given the velocity and initial position function of a body moving along a coordinate line at time t, find the body's position at time t, right? Position function. So solution here. Start by saying that the position function has to be equal to the antiderivative of the velocity function, right? Because we're going backwards. But now they are giving you this velocity function, is this, right? So we have to integrate or take the antiderivative of this velocity function. Okay, now distribute your antiderivative, right? What should be the antiderivative of this? Well, let's write it out here so I can follow, plus antiderivative of 7 dt here. Now, constant negative 13 comes out. I focus on taking the antiderivative of this part. And for this guy, same idea. Constant 7 comes out. I focus taking the antiderivative of 1 here, constant function 1. So S should be equal to what? Minus 13. This antiderivative, knowing that the exponent is 1 here, is equal to this t squared over 2 plus 7. Remember, antiderivative of the constant function 1 is just identity function, so t, right, t. And remember, plus a constant. So almost done, right? I got the position function. What is bothering me is this constant that we don't know what is equal to. But that can be taken care of by looking at this condition, right? S evaluated at 0 equal 13. This is telling me that the function in one hand evaluated at 0 should be equal to this, minus 13, 0 squared over 2 plus 7 times 0 plus a constant, right? On the other hand, they are saying that this is equal to 13. So let's do the math. 0 squared 0 times 13, 0. 0 times 7, 0. So this is C equal 13. Once you have this, go back to S and finally write out your position function completely determined. Look, 7t plus 13, right? This is it. Okay. So here it took just one integration, okay, in order to solve this problem. But there will be times where it will take two integrations. I will show you next. But first, I want you to practice on this part. Let's go to the exercises here. This one. Can you try this one? They are telling us that the velocity function is minus 14t plus 10. And they are saying that the position function evaluated at 0 is 11. They are asking us to figure out what is the position function. So let me give you this hint. S is the antiderivative of the velocity function, right? So start integrating this. Once you integrate this, once you take the antiderivative, right, you will have some constant added to your result. To find that constant, you use this, right? Use this. Can you try this? Okay. Right. Also here, distribute the integral, right? So distribute this. Yeah, it's a very classic initial value problem in physics, right? I think rectilinear motion. I see students figure this out. Very good, very good. Let's check. CG. Very good, very good. Excellent, excellent. Also, CG has posted the answer, right? Yeah, integrate, then using the extra information there, find the value of the constant, and then you should be able to write out your answer. Okay, so let's explain this, right? Let's explain this. Yeah, let's explain. Very good. If you distribute your antiderivative here, you're gonna get that S is equal to antiderivative of this minus 14 t dt plus the antiderivative of 10 dt, right? Taking this constant out, this will be minus 14 integral or antiderivative of t dt plus constant out, what is left is 1 dt. This guy, more students are posting answer. Since has exponent 1 using the power rule, its antiderivative is t squared over 2, right? T squared over 2 plus 10. Antiderivative of constant function 1 is the identity function t plus a constant, right? Plus a constant. This is the value of S, the position function. and simplify this S is equal to minus 7t squared plus 10t plus a constant, right? Okay, great. Now, in one hand, S evaluated at 0 is this, negative 7, 0 squared plus 10 times 0 plus a constant, right? This is 0, this is 0. But on the other hand, this is equal to 11. So this is telling me that C here is equal to 11. Right away, once you find the value of C, replace it into your position function, and your position function will end up being 7t squared plus 10t plus 11, right? Very good, guys, very good. So that's for number 9. The answer, therefore, for number 9 is just this A. Very good. Excellent. Yeah, now, this one is similar. You can do it at home. I'm going to show you now how to deal with this form, okay? What to do when they give you acceleration, and from there they want you to retrieve the velocity and then retrieve the position function. Yeah, Sarah, very good. Grace. Yeah, Adriana, right? Yeah, very good, guys. Very good. This was a nice problem. So we know how to do it, right? But now let's take a look at this form, right? This and this, and see how they go. All right, so let me give you an example for that. Sometimes you might have to do this process twice. For example, check this out. Example 5 is telling us that given the acceleration, initial velocity, and initial position of a body moving along a coordinate line at time t, find the body's position at time t. Acceleration, original acceleration is 9.8. The velocity evaluated at 0 is 8. The position function evaluated at 0 is negative 6. So they're giving you two conditions now, right? This as before, right? But in addition to that, they are giving you now this condition. And of course, they're giving you the function, which is this constant function that we're going to integrate, right? All right, so start by going backwards from acceleration to velocity, right? So go backwards from acceleration to velocity. So that is accomplished by doing this. Velocity equal the integral or the antiderivative of the acceleration function, right? dt. But they give us the acceleration function there. Look, it's 9.8. 9.8 is a constant function, right? Yeah. But we're gonna take the antiderivative of this. So now, taking the antiderivative of this, remember, constants, they come outside of the integral. So we are left with this 1 dt. This is the constant function, right? And when you take the antiderivative of the constant function, what you get is the identity function, right? T here, and then plus a constant. Look, I was able to retrieve or to get from the acceleration the velocity, right? This is the velocity function. Now, since this is a constant that may be different than the constant I'm going to get later when I retrieve my position function from the velocity function, allow me to call this constant C1, right? So C1. All right, but now in one hand, they are saying that this velocity function, when evaluated at 0, should be 9.8 times 0, right? And substitute t for 0 plus constant 1. This is 0. On the other hand, they're saying that the evaluation at 0 for the velocity is just 8. So 8 here, 0 here. C1 equal to 8. C1 equal to 8. Well, then I can substitute this in here and claim that I have found completely, right? I have figured out completely what is the velocity function. It's 9.8 times t plus constant 1, which is 8, right? This is 8. Done with the velocity. Completely determined here, right? Now, it's not over because I have to find now the position function, right? At any time. So now take this velocity function, integrate it, and go backwards to the position function, right? So take the antiderivative of the velocity to go to the position function. So now I have there this should be equal to the antiderivative of 9.8 times t plus 8 dt here. This is s, right, position function. Now distribute your antiderivative over. So s will be the antiderivative of 9.8t plus the antiderivative of a dt here, right? All right, so in order to take this antiderivative constant outside 9.8 inside t dt plus constant out 8 inside the antiderivative constant function 1 dt. But now what is this guy? 9.8 integral of t dt, since this exponent is 1, is t raised to 1 plus 1, 2 divided by 2 plus a times the integral or the antiderivative of the constant function 1 is the identity function t, right? Plus a constant. Since I don't want to confuse this previous constant with this new constant, let's call it C2. Okay, but now I have this function, right? So let's continue here. Now S evaluated at zero in one hand should be this, right? This into this, let's simplify, it's just 4.9. So the evaluation of the function at 0 should be this in one hand, right? 0 squared plus 8 times 0 plus C2. This is 0, this is 0. On the other hand, S at 0 is -6. They are telling you that. So it turns out C2 equal -6. Once you have the value of C2, replace it here. And then you will have your position function finally look recovered completely. So S will be equal to what? 4.9 t squared plus 8 times t plus C2, which is -6. But we know that negative multiplied by positive is just negative. So finally, this should be your position function, right? Which was recovered from the acceleration and from the velocity gradually, right? In two applications of these antiderivatives. Okay, guys. All right, and then this will be the hardest probably because we're not gonna do it 3 times, 2 times maximum, right? So up to here. All right, so now I want you to practice in this form. So let's go to our worksheet here. And let's do this too. Number 11, can you try this? I will give you the hint. They are saying that given the acceleration, initial velocity, and initial position of a body moving along a coordinate line at time t, find the body's position at time t. They are giving you the acceleration function. Is this a equal 20? Is a constant function, right? And together with that, they are saying that the velocity evaluated at 0 is 17. And the position function evaluated at 0 is 3. The challenge is to figure out first the velocity and then the position function, right? Completely. So as a hint, I'm going to give you this. The velocity can be recovered or obtained from the acceleration by integrating it with respect to t, right? By taking the antiderivative of this, right? So start by taking the antiderivative of this constant function. Then you're going to get some constant, call it C1, or if you can handle calling you constant C, if you know what you're doing, you can call your constant just C and find it twice. But to avoid confusion, probably you should call it C1, then C2, right? Find the constants, retrieve the velocity, and then retrieve the position function. I see. Yeah, and try to catch some patterns here, right? In physics, often, um, since by experiments they determine initial values, right? The constants that you get, they end up being these numbers. You might have noticed, right? Before, in some problems that we did before, since they were not related to the real world, it was not the case. But in physics, this is something that happens very, very often. So try to catch that. CG. Let me see, CG. If you figure this out, 11. CG, I think you need to adjust. I think one of the constants was not accurate. Yeah, so number 11. Mhm. Yeah, Oscar. Yeah, you made my day. Yeah, Oscar, very good. Sarah, Grace, yeah, very good, guys. Excellent, excellent. Yeah, it takes a while, but yeah, very good, very good. Sarah, Oscar. Um, it's try to catch this pattern in real world problems, right? The initial values determine the constants, right? So these two guys determine the constants. So follow that. Yeah, very good, guys. Very good. Yeah. So let's do it together, right? Let's do it together. More students are posting more answers. Adriana, yeah, no, very good, Adriana, very good, very good. Yeah, it's just takes a while, but again, helps to know that the constants will be these numbers for this type of problems, right? Physics. If not, it might not be the case. That's good to know this. But see, no, correct. Very good, very good. Very good, very good, very good. So let's do it together, okay? So we're going to start by taking the antiderivative of the acceleration function, which is 20. That can be done by taking this constant 20 outside of the antiderivative, outside of the integral, right? Yeah. What is left, Professor? One. The constant function 1 is left, right? But now, not hard to figure out that this is equal to this 20. The antiderivative or integral of constant function 1 is just the identity function, right? T. But there is a constant there, right? I know I'm going to do this process twice, so I'm going to call this constant 1, so I don't get confused, okay? Now, this is a function. In one hand, they're saying that the evaluation of this function at 0 is this, right? Is this. But on the other hand, they are telling me that somehow, via experimentation, perhaps, they determine that this initial value function, the initial value for this function velocity is 17. This is 0, right? This tells me that the first constant, 17. So there you see the pattern, right? The first constant ends up being this, right? Very good. Yeah, now this should be substituted here right away as you find it, right? So then you completely determine your velocity function, 20t plus 17. Now, but it's not over because you gotta go now from the velocity function to the position function, right? Position function. So then we have to integrate again or take the antiderivative of the velocity function to get the position function. So this is going to be integral of 20t plus 17 dt, right? Distribute your integral, right? Take the constant outside, you will end up with this, right? For this part, plus take the constant outside 17, you will end up with the antiderivative of the constant function 1 there. Well, what is this? This is going to be 20. T has exponent 1. So using the power rule, this should be t squared over 2, right? Plus 17. the antiderivative of the constant function 1 is the identity function t, plus a constant. I will call that constant C2, okay? Simplify S equal 10 t squared plus 17 t plus constant 2. Now it's time to use this extra information, right? They are saying that the evaluation of this function at 0, which is this, right, in one hand, should match with the following number. Look, this they're saying should be 3. Good news here, this is 0, this is 0, so C2 equal 3. Again, right? Do you see the pattern there, guys? This number 3 ends up being the constant, right? Very common in physics. All right, so then quickly you put this into your position function, and what you gain is that now you have your position function completely determined. So it's no longer a family function, it's this unique function, right? Very good. And then if you look through, this is here. You follow it? Very good. All right, try to do this one now to complete this. This one is a little bit different, but as a practice, right? Try to do this. Do this one. I'm gonna write out the information here. They say that the acceleration is a constant function a equal 10. The velocity evaluated at 0, physicists call it initial velocity, right? It's 11. Initial position at time 0 is 2, right? Combining these 3 pieces of information, figure out what is the position function, right? And I will write out here the first step, which is to go backwards from the acceleration to the velocity via this process of integration, right? So start with this and then continue, guys. Continue there. Find that integral, the antiderivative, then the constant, first constant, and then integrate again what you got, and then find the second constant. And the hint again, right? Worth it because it's always good to catch patterns, right? Good patterns, especially. The hint, these numbers are not just any numbers, and they end up being the constant, right? Yeah, you should know that. In physics, very, very common, but not always we saw it, right? Be careful. Let's see, CG. Check C. CG. Yeah, you made my day. Very good, very good. Yeah, you got it, Yeah, very good, very good. More experience. Posting more answer. Yeah, try give it a shot. It's not that difficult. Grace. Yeah, excellent. Excellent, Grace. Yeah, very good, very good. You got it. Yeah, Sarah. Good, good. Yeah, and again, it's a nice application of antiderivatives, right? How to recover the position from the acceleration, from the velocity. All right, guys. So let's figure this out together. Okay. Yeah, very good, very good. So we start again going backwards from the acceleration to the velocity, right? By this process of integration or antiderivatives, right? So we have to take the antiderivative of this, take your constant out. The constant is 10. What is left, Professor, there? What is left is 1 dt, right? The constant function 1. Now, this becomes 10 times the antiderivative of the constant function 1 is the identity function, right? Because the derivative of t is 1. Very good. So that's that. But I have to consider a constant. I'm going to call that constant C1. All right. Now, take advantage of this information, right? They're saying that the velocity evaluated at 0, initial velocity is how physicists call it, is 11. So the velocity evaluated at 0 in one hand using the function is this, right? But on the other hand, using this information is 11. So 11 must be equal to this, 10 times 0, 0, C1, 11, right? Again, right? The 11 ends up being the constant one. All right, so now, if you go further, now that you know the constant, put it here, and then you will see that your velocity function is completely determined, is 10t plus the constant 1, 11, right? Is this. But it's not over because we have to find now the position function s, right? S. And that can be gotten by integrating or taking the antiderivative of the velocity function. Yes. We have the velocity function here. That is 10t plus 11 dt here. Now let's take the antiderivative there. Antiderivative of this is going to be 10 comes out, t stays dt plus 11 comes out, integral of constant function 1, right? S equal 10 times what? This guy has exponent 1, so it should be t raised to 1 plus 1, 2 divided by 2 plus 11. The antiderivative of constant function 1 is just the identity function t. I need a constant. I don't want to confuse my constant with this constant. I'm going to call it C2. Now let's use this extra information, right? That is given to us this part. They're saying that this position function, when evaluated at time 0, this is what physicists call the initial position, right? Or yeah, initial position at time 0. This using the function is just this, right? 5, 2 into 10 is 5. 0 squared plus 11 times 0 plus C2, right? Good news, 0 as a multiplier is so nice, you know, eliminate these two terms. But on the other hand, they're telling us that this is equal to 2. So conclusion, C2 equal 2. Again, guys, the pattern still holds, right? Remember we said this guy is not just any number, it's that ends up being the constant, the second constant. So now you can write your position function as not as a family of functions, but as a unique function, right? Completely determined as this. 2 into 10 is 5, t squared plus 11t plus C2, but C2 is 2, right? This is it. Good, looking through now for 12, you can see that is here, 5t squared plus 11t plus 2. Very good. Always be careful when you choose your answer, guys. They're very close to each other. Look, go there, right? 5t squared plus 11t plus 11t plus 2 plus 2. Sign and quantity should match, right? Very good. Okay,